that foundation of mathematics and with respect to deep learning, and we have seen that deep learning introduction also. So yesterday I had just given a bird view of deep learning. So what are the models are there, what are the types, and what are the applications of the deep learning. Today we are going to in deep. So we are going to see about how two basic models of deep learning, convolutional neural network and the recurrent neural network, will do for how we can apply those two models for cybersecurity. So now I hand over to Shahinaa ma'am. So ma'am, you can continue, ma'am.
Okay, sir. Thank you very much, sir. Good morning, everyone. Am I audible? I hope I'm audible to all of you. I begin with a sorry for a delay because there were some hiccups from my side. So let's begin. The topic that I'll be talking on is convolutional neural networks and recurrent neural networks for cybersecurity. It will be slightly tangential but very relevant to the workshop that you guys are having, the course that you're having. In that it is not so much on cybersecurity, but more on, the focus is more on convolutional neural networks and recurrent neural networks. And of course, we'll see a couple of more case studies on how we use these two neural networks for cybersecurity. Okay. So, so this is going to be what I'm going to speak on. So I'll be giving you an introduction to deep learning and just mention their applications for cybersecurity. We'll focus on, next we'll be focusing on convolutional neural networks and the working of a CNN. And then we'll look at a case study of how we use CNN for cybersecurity. Then we'll move on to recurrent neural networks, and we'll understand the different architectures and how you use recurrent neural networks for various applications. And we'll take up a case study on how to use RNN for cybersecurity. Okay. So as I said, this is a tangential talk in that we'll be focusing on CNN and RNN. And we'll just take up a case study for briefly on how we use them for cybersecurity. So see, actually, if you are all that you're interested in cybersecurity, then people treat CNN and RNN as a black box. You have platforms available where you can just treat it as a black box and just give in your input and get an output. But the idea here is to understand to unravel the black box. Okay. So this you must have seen, but just as a brief, how does deep learning help in cybersecurity? So these are some of the applications that are there. One thing is an intrusion detection and prevention systems. Okay, you can build deep learning based intrusion detection systems. And the second application is malware detection. So you have deep learning algorithms which are far more better than the traditional firewalls, wherein the traditional systems, they are dependent on known signatures and they look for common attack patterns. But if you don't have a common attack pattern and you don't want to rely on signatures, then you can think about using deep learning algorithms which work better when you have advanced threats. And of course, there is spam detection. For example, Google already is doing a 99.9% spam detection for you. So 99.9% of the spam is already not coming to your inbox, mail inbox. But now what they have done is they've used deep learning and they have removed. They say that they remove of the order of 100 million spam mails from reaching us per day, in addition to the 99.9%. Okay, so the fourth application is network traffic analysis for malicious activities. And the last thing is, so all of these, so far what we've seen is they are coming from external sources, okay, malicious external sources. But what if your internal source itself is malicious? So then, for that case, you need to know as the lead of an organization, you would like to know the user behavior analytics of the your own employees. So you would so that if they want to use their legitimate access with a malicious intent, then you can prevent that. So these are some of the applications where you use deep learning for cybersecurity, and that is why this is relevant. So what I'll do is I will briefly take you through the beginnings of deep learning. I think this is pretty important. Even if you might have gone through this earlier, I think that we'll just brush through quickly. Okay, so I have to mention two guys here, Warren McCulloch and Walter Pitts, McCulloch and Pitts, because they, if at all we want to say father of neural networks, these are the two guys, because they came up with the revolutionary idea saying that neural tissue, think about our biological neural tissue as a circuit which performs mathematical computation. When they came up with this idea, it revolutionized the way we think about biological neural networks. So this is the biological inspiration for artificial neural network, which is the biological neural network, and the fundamental unit being a nerve cell or a neuron. Okay. So then, when we look at the typical neuron, you have inputs. You have a cell body which does summation of these inputs, a weighted summation of these inputs, and the output of that particular neuron. Just three parts that you need to know. One is the input, the second is the cell body which does the weighted summation, and third is the output. So if I want to build a artificial neural network, first of all I need to model a single neuron, and then from there build a network. So if I know these three things, input, cell body, and output, I'm ready to model a neuron. This is the model of a neuron. I have inputs and I have to weigh them. So I have weights associated with the inputs. So I get my cell body is, yeah sir?
Yeah.
Yes sir?
Yeah. Participants could
yes,
see
sir.
only the first page of the slide, first slide, because you have to prompt the organizer to move your slides forward.
Okay. I'm very sorry. I'm very sorry. Yeah. Yes, sir. I just slipped that. I'm sorry. Go to the second slide. The second slide talks about the organization of the talk, which I just mentioned.
Yes, ma'am.
And then the third slide,
one point from my side.
the different applications which I just mentioned, intrusion detection.
Yes, sir. The Java application. You see the Java application slides. What our ma'am is sharing. Can you see the slides? No.
Come again, sir.
Can you see the slides? No, Shika's slides.
Yes, sir. I am seeing the slides.
Yeah. From there, you try to present from this slide, ma'am. If you want to go to the next slide, you just inform us.
Slides. Okay.
Yeah.
Okay, fine, sir. Okay. All right. So please go to the third slide. Yeah. So these are some of the applications which I just mentioned: intrusion detection, malware detection, spam detection, network traffic analysis for malicious activities. So all these four are for, as I said, for external malicious activities. What about insider malicious activities? For that, you have user behavior analytics. So all of this, you use deep learning for cybersecurity, for different cybersecurity applications. The next slide, please. So these two guys we credit for the revolutionary idea that nerve tissue can be thought of as a mathematical tool that does computations. Okay, so the next slide. This is just a dedication page, and this is, as you know, the inspiration for our artificial neural network. You have a network of biological neurons or nerve cells, which makes us such fantastic, complex pattern recognition systems that we are. The best pattern recognition systems that are there in the world are humans. So we try to mimic our computational ability. We might not be great in speed. We are far lagging in terms of computational speed. We cannot compute with the computers. But in terms of pattern recognition, there is none to beat us. So our biological network is the inspiration for the artificial neural network, and hence the deep learning neural networks. So if you look at a typical neuron, you have just three parts. You need not know anything else. Just three parts. You have inputs, and a cell body which takes in inputs and sums them up, and the third thing is the output, which if the weighted summation exceeds a particular threshold, then it will fire. So these three parts, if you know, then you're ready for modeling a biological neuron, and hence from there build up a artificial network, neural network. So please, the next slide. So we have modeled, in the next slide you can see a model of a single neuron. So you have inputs, the xi's are the inputs, and I said that they are weighted. So you have weights associated with the inputs, and if you like to know what these weights represent, they represent the synaptic strengths in our biological neural network. So the interconnection between neurons has something known as the synaptic strength, and as we learn something more and more, this synaptic strength keeps getting better and better, and so we capture that synaptic strength in terms of weights. So we have weighted inputs coming to the neuron, and then you do a weighted summation. That weighted summation is sigma wi xi. Now, that alone doesn't become the output. What you do is you take this weighted summation, sigma wi xi, which I call it as z, and then you give it to some activation function. The activation function, which was very popular, is known as the sigmoid function, which you can see on the screen. So the sigmoid function is like the S shape. So that gives some amount of nonlinearity to the input. Otherwise, sigma wi xi is simply a straight line, and having a straight line as an output of a neuron will not help us at all. A linear neuron is not going to help us in learning any complex pattern. If you want to learn any complex pattern, we have to have this G of Z. This G of Z is a infuses a nonlinearity, and this specifically, if I'm using sigmoid function, then G of Z becomes 1 by 1 plus e power minus z. So that is that S function that you can see on the screen, and so you have this output. G of Z becomes the output of a single neuron. Now we modeled one neuron. From there, next slide please. From there we build on. So this is just a quick flow. I just want you to see like how mathematically it works. So I have a input vector, you can see on the left side, and weights W1, W2, W3, and let's see what happens. The next slide, the next few slides in quick succession, you can see that Z, I compute simply sigma wi xi, and then we compute G of Z. You can see on the top screen, 1 by 1 plus e power minus z. And what advantage of this G of Z does is, see, this Z can be any large positive number or it can be a large negative number. Now what G of Z does, if I'm using a sigmoid function, it squishes the values between 0 and 1. So if my Z, so if let's say that I'm talking about a classification, and let's say that I'm talking about malware. I have just two malwares and I want to classify whether it is, or just I want to classify whether this is a malware or a benign software. Okay, so it's a two-class classification problem. In that case, my output should be either 0 for one class and 1 for another class. So if my G of Z is any large positive number or large negative number, there's no way I can compare and say that this Z corresponds to this malicious class or a benign class. So for that, G of Z helps me. What it does is it takes that Z, which can be any large number or a very small number, and it squishes the value between 0 and 1, as you can see in the graph above. So when it squishes and I keep a threshold at 0.5, I can safely say that if G of Z exceeds 0.5, then it belongs to malicious class, and if it is less than 0.5, it belongs to benign class. All right, so next slide please. Yeah, so then what I do is, one single neuron doesn't help me, so I have to stack them up. So I've stacked them up to I've stacked them up to get one layer. So the input layer you can see actually two layers, an input layer and output layer. Input layer is simply a fan out layer. It doesn't do anything. So you just have the output layer, which is all where the computation happens. So such a structure, so it's basically there is only one layer of computation happening. So I give my input values and then I get the output. Input, what are the input values? It can be anything. It can be a raw data, it can be a raw image data, it can be a raw speech file, it can be a raw text data, or it can be some features that have been extracted from these raw data. It can be anything, some n-dimensional vector that I have as input. Okay, so I give these inputs and there's only one processing layer, and that's called a perceptron network. Next slide, please. Okay, so now we want to use this. So what we've done is we've seen what is a single neuron, and then we've seen how we stack them up to form one layer of neural network, and we call this one layer of neural network the perceptron. Okay, and then see, the whole idea is trying to make this artificial neuron learn exactly the way we learn, exactly the way our biological neural network learns. So when we say learning, we're talking about adjusting the weights, adjusting the parameters here being weights. So when I keep on iteratively presenting the input and I keep adjusting the weights, remember I talked about the weighted inputs, the wi, w1, x1, w1 and w2 and w3 and so on. So those are the weight parameters I need to adjust. And I remember once again that these weight parameters correspond to the synaptic strength of our biological neurons and all the memory that we learn when we learn something and we're learning something new. See, you're listening to my lecture as you are assimilating whatever I'm saying, but at the same time you don't forget what was already taught to you maybe in the last few days or the last few years. And that's because we do not store it in our processing units like in our computers, but we distribute it and share it in our synaptic strength, and that is what makes us such fault tolerant beings, fault tolerant pattern recognition systems that we are. So coming back, we're talking about adjusting the weights. So so that is what means by when we say learning in for a neural network. So how do we learn how do we train, or it's also known as training or learning, both refer to adjusting the parameters, here the weights. So what we do is we simply start where you begin. First iteration, W's will be random values. Then what do? You just pick up a pattern from the training set. Feed. When I say pattern, I'm talking about an input n-dimensional vector. Pick up a pattern from the training data set that you have, give it to the network, calculate the output, you'll get some output. What you will have in the training set is a pattern pair. When I say pattern pair, I'm referring to an input vector and a corresponding class label. So that would be my typical training data set. So for every input vector, I will have a corresponding class label. The class label refers to the desired output. All right. So now what happens is you give this input pattern to the network. The network will give me some output, and that output I'll compare it with the desired output. The desired output, which is already available to me as a class label. Now this error, there will be an error, and that error in that equation, if you can see, is called del. Del is the error. Sorry, E will be the error between the actual output of the network and the desired output available to me as it's a training data set. Then what do is I will differentiate this error with respect to weights. Why am I differentiating that? I'm differentiating that, and you can see that there is a negative sign there, and I'm differentiating it. That negative sign and differentiation helps me to minimize the error. Okay, I'm not going into the technicalities. Just know that when I differentiate it and I'm taking the negative value, I'm going down a slope. If you can imagine a bowl, okay, some bowl in the kitchen. So you can see a smooth descent from the rim of the bowl to the bottom of the bowl. So that descent, if you can want to call it, you can call it as a gradient descent. So that dou E by dou Wj is simply a gradient descent. The negative sign tells me that I am descending, and eta, that parameter eta, helps me to understand, or it rather controls how my descent is going to be. If my eta is large, then the descent is going to be very quick. If eta is small, the descent will be slow. So now what we're doing is we're adjusting the weights. So this is the weight adjustment. So we'll take this del W and subtract it from the current weight, and then that is going to be my new weight, and then I'll keep, so now the weight adjustment has happened, give a new pattern and repeat the whole process iteratively. That is learning from a perceptron, learning a single layer perceptron. Next slide please. But when I do this, there is some limitation in, next slide. Next slide. Yeah. So there is a limitation. The limitation is that it can solve problems only which are linearly separable. Note that if you remember perceptron, if you remember a single neuron, it gives me a straight line decision boundary, and on all that the activation function does, it just helps me to tell that what is above on one side of the straight line decision boundary belongs to one class, and on the other side it belongs to another class. So it's a straight line decision boundary, and the problem is that perceptrons, the single layer perceptrons, they can help in solving only those problems which are linearly separable, meaning all the classes, all the patterns, or all the 10 examples belonging to different classes can be separated by a straight line decision boundary. I'm not going through the examples here. For example, if you want to implement an AND function or an OR function, you can clearly see that there are two separate classes here, and you can simply draw a straight line decision boundary to separate the classes. So perceptron can be used to solve such problems. And on the last one is an XOR problem, which as you know, it cannot be separated by a single straight line. So a single layer perceptron will not solve such problems. Let's go to the next slide. So this is an example where I have two training examples of two classes which can be separated linearly. So I can use a perceptron here. Next slide. And here I can see that they are not linearly separable, and I cannot use perceptron. So that is a limitation. And for your information, all the real world examples are non-linearly separable. This is a very beautifully non-linearly separable simple case, but otherwise they are so complicated that you just cannot come up with a straight line decision boundary. Next slide. Next slide, please. Yeah. So the one before. The one before. Yes, ma'am. So what we do is, I can't do with a single layer perceptron. So the idea is add more layers. Okay. So now I have two layers. So I have a hidden layer which is in between and an output layer. So now this is a two-layer perceptron, multi-layer perceptron, and so this solves my problem in that it starts giving me complex decision boundaries. Next slide. Next slide. Yeah, I'm just taking an example. So I have input vectors here under the column fields, and then I have the corresponding class labels. So you have a two-class classification problem. One set of examples belong to class 0, another set of examples belong to class 1, and so on. And this is what you're seeing in the network is a two-layer perceptron, or it's a multi-layer perceptron, and this overcomes, as I said, the linear separability problem. The output of such a network would be a complex decision boundary, a non-linear decision boundary. Okay. So next slide. Next slide. Next slide. Yeah. So you can see that I'm taking one training example, give the input, okay, and the class label is 0, but I'm getting 0.8. So I compute the error, and I use that error and back propagate it to adjust the weights. Next slide. Yeah, next slide. So you can see the as you go down one or two slides, yeah, you can see that the weights are getting adjusted. Yeah, next slide. Yeah, so then what I do is I've adjusted the weights. Once I've adjusted the weights, I'll give a new training example. Now I can see that training example corresponding to class label 1. I will present that input now with the adjusted weights. Next slide. Yeah, so the output I'm getting is 0.9. So that it will compare with 1, and then that error, you will differentiate that and use the same formula, and then you will back propagate it and adjust the weights, and you will keep continuing this for some number of iterations. Okay, so next slide. Next slide. Yeah, so you can see the weight adjustment happening. Next slide. Yeah, so how many times will you keep repeating it? You'll just keep repeating it so many times until you are satisfied that there's no further change that's going to happen, and that's when you say that your network is converged and you stop that. Okay, so the next slide. Yeah, so what you'll see in the next few slides is, as if you can run it through in quick succession, you can see that for every iteration they keep you can see that it's a two-class classification problem, and you can see a decision boundary. So this is after one iteration, this is the decision boundary that you get. Okay, so then if you run through the next few slides with a similar figure, you can see how the decision boundary keeps getting adjusted. So you can see the decision boundary, they keep on getting adjusted. You see, this is the fine. This is the decision. Finally, once your training is done, no ma'am, go back one slide. Yeah, so this is the final decision boundary that you get. You can clearly see that it is one thing is that it's a non-linear decision boundary, and which the multi-layer perceptron gives me. And the second thing is that you can see that all the training examples have been perfectly classified, the yellows and the blues, as two separate classes. Okay, so the next slide, please. Right. So this is the point I want to say. So what you do? So this non-linearity comes from my sigmoid function, using sigmoid function as my activation function g of z. So that gives me the complex decision boundary. So what is very important is, at this point I just want to make a research point. That is that when you get the decision boundary, what is very important is it should not be so underfitting that you're not even able to do classification properly. On the other extreme, it should not overfit the training samples. It should just be enough to generalize. Okay, so we want a network that generalizes well. Neither underfitting nor overfitting should happen. Next slide, ma'am. Yeah, so just a point here, I just want to compare. We said that perceptron has a linear decision boundary. It doesn't do a good job. So we have multi-layer perceptron, which does a good job by giving us complex decision boundaries. As a contrast, we have you've heard of support vector machines. They also give linear decision boundaries, but they work fantastically well. Sometimes better than multi-layer perceptron itself. You might ask how. Perceptron gives me a linear decision boundary, that's bad, but SVM also gives me a linear decision boundary, but that's good. That's because this does a very neat trick. What it does is it takes the training samples and then throws the samples into a higher dimensional space. Because let's say that I have an n-dimensional training, and all the training vectors are n-dimensional. Let's say whatever that n can be, 100, 200, whatever. Take that and throw it to a much higher dimensional space. So what happens is that space is the data samples will simply spread apart because it's a higher dimensional space. It becomes sparse, and then it becomes easy to come up with a linear hyperplane in that higher dimensional space. And that is the neat trick that SVM does through kernels, and it gives fantastic results. That's why it's a very powerful classification tool. Next slide. Yeah, so basically what neural network does is it extracts features. Okay? It extracts features. For example, this is the image, using an image of, I want to do classification of numbers from images of numbers, and then we just feed it to a neural network, and all it does is it detects features. Next slide. Next slide. Yeah, so what I want to bring out here is, if I have, let's say, some number of, let's say I have two hidden layers, or let's say two hidden layers and an output layer. Each hidden layer starts extracting features. The initial hidden layers will extract the lower dimensional features, and as you keep proceeding, the next layers will start extracting the higher dimensional features. So the lower, the features of lower granularity will be extracted in the initial layers, and the grosser information or the higher dimensional aspects will be extracted in the latter layers. Next slide. Okay, so we can see that multiple layers make sense. It makes sense to have multiple layers. So then so when they started seeing the power of having multiple layers, they decided that yes, this is nice to have, keep on adding more and more layers, because multiple layers make sense. And that was the idea for going for deep learning neural networks. Next slide. Yeah, so this is how the brain also works. Starting from, let's say, for example, from the visual stimuli that we get from eyes sensors that we have, starting from there, going all the way up to the brain, we have multiple layers of neural networks, and we have a hierarchical organization which starts from simple cells and goes all the way to complex cells as we reach the brain, and and this is exactly the way it operates. So this is what we're trying to mimic. Next slide, please. Yeah. So so then what happens is we have a large number of hidden layers. We have the same multiple layers of perceptron. We don't call it multi-layer perceptron anymore. We call it deep neural network. Okay. Just take a multi-layer perceptron and add more add more hidden layers. You will get a deep neural network, a fully connected deep neural network. Okay, next slide. All right. So, but then our simple weight learning algorithms will not work here. So we need to have something, some tricky solutions. For your information, the algorithm that adjusts the weights, or in other words, that causes the learning to happen in a multi-layer perceptron, is known as backpropagation algorithm. Right? So next slide, please. Right. So we have deep learning here. So we're going to start our deep learning from here. So the next slide. So all along we've been building the background for why we are learning what we are learning. So this slide, I thought it's very important for you to know. See, you might want to go for, suppose you're doing some research, or doing some project work on trying to use machine learning algorithms for or deep learning algorithms for your cybersecurity applications. Let's say that you have a small data set and you're using deep learning as well as machine learning algorithms. Sometimes the machine learning algorithms will give you better performance than deep learning. You cannot claim that machine learning is better than deep learning. All that you can claim is that because my data set is small, as you can see the left side graph, you can see that when your data set is small, the machine learning algorithm and deep learning algorithms have similar performance. Right? Okay. So then, but if you have humongous amount of data, which is available to us today, okay, when you have humongous amount of data, you can see the performance, the accuracy that you get with deep learning far exceeds the traditional machine learning algorithms that you have. And deep learning helps us when we have humongous amount of data. Next slide, please. All right. So now what we'll do is the next the next some number of slides. Sir, how much time do I have? Anand sir, how much time do I have? Hello. How much time can I take, ma'am? Shika, can I continue the presentation?
Yeah.
Please continue.
Yet.
Yeah, you can continue. I think for your session you have around 10 minutes now.
Shika, I would like to continue.
Yeah, please continue. For your session, ma'am, as per schedule, you have around 10 minutes.
They said that I can continue, so I just want to, yeah. Well, it's breaking terribly. Shika, can you repeat that?
Ma'am, you can continue as for now. For your session, you have around 10 minutes.
Hello? Can I have my presentation?
Why?
Because that's, but I remember Jyoti sir and Anand sir asking me to continue. So probably I'll continue till 11 o'clock because they wanted me to take for 1.5 hours. So I just wanted to check up with them. Okay, probably they're not available. Okay, I'll
Yeah,
just
yes, ma'am.
continue.
Yes, ma'am. You can continue. Ma'am.
So we're moving on to convolutional neural networks. So if you look at, yes, sir. Okay, sir. I have time till 11 o'clock, sir.
Yes, ma'am.
Okay. All right. So let's just continue our. Yeah. Okay, sir. Fine, sir. Let's continue our discussion. So what we will be seeing in the next some slides is we will be discussing convolutional neural networks and we will be looking at recurrent neural networks. The traditional applications. So that will be a tangential discussion before we move on to one case study for each. Right. So if you look at convolutional neural networks, some of the applications for which they work great is image classification, object detection, neural styles transfer, to name some. The difference between image classification and object detection is that image classification is classifying whether the image contains a dog or a not. Okay, so it can be a binary classification problem where I'm giving you a set of images. You have to say whether the picture contains a dog or not. That is image classification. Object detection is in your autonomous cars, for example, you have to have this. So you should tell, given a picture, you should tell where each object is. You should draw a box on each object and tell that the dog is here, the bridge is there, and so on. This is very useful for autonomous vehicles. Right. So and then of course neural style transfer. If you're very bored of seeing Mona Lisa in the traditional garb that she is, you can just have modern art imposed on her image, and you can do a neural style transfer. Okay, so this is some of the applications of convolutional neural networks where they work very well. Okay, so actually cybersecurity applications are much later applications of deep learning. These are the traditional applications where they work very well. So what we'll do is we'll try to understand how CNN works. Next slide, please. Right. All right. So now the question begs is that I have a multi-layer perceptron, right? And I can give input as any image. What's the problem? Why should I go for CNN? Right? Let's understand why CNN is so powerful compared to a traditional multi-layer perceptron. Let's say that assume that I have a 64 cross 64 cross 3 in RGB image. Right? The 64 cross 64 is my image, 2D image, and the 3 refers to the 3 channels R, G, and B. Right? If this is my image, then I have 64 into 64 into 3, that is about 12,000 input features. Right? What if I have a 1000 cross 3 RGB image? In that case, I'll have 3 million features. Right? 3 million features. And assume that my first hidden layer has 1000 neurons. My input will be 3 million dimension. My first neuron will be, my first hidden layer will have 1000 neurons, which means that the number of weights that I will be looking at between these two alone, that is the weight matrix of the first layer alone, will be 1000 cross 3 million, which is 3 billion parameters. Now that is very, very large. 3 billion parameters to train in that layer alone is pretty large. See, if you can talk about, say, one important point I want to bring here is, I have a training data set. Let's say I have 1,000,000 images. 1,000,000 images is quite a large data set, right? Or even 10 million images. But I'm having 3 billion training parameters in the first layer alone. Hello?
Hello, ma'am. You continue, ma'am. You continue, ma'am. I'll share the screen. You continue. Can you see the screen?
Yeah, I'm waiting for the
Screen. It's loading. I think.
The screen is not there.
Yeah. Now, ma'am.
Yeah.
Yeah.
Yeah. Please continue, ma'am. I'll take care. Shika is leaving. I'll take care.
Yeah, I can see. Perfect.
Yeah. You continue.
Sure. So, so now the problem is that, yes, sir. The problem is that we have the training parameters of the network are far larger in the billions compared to the data set, which is in millions. Okay, I have a large data set, but I have a much larger number of training parameters. What happens is, when the training parameters far exceeds the training examples, then I'll have a problem of overfitting. When I say overfitting, the network will be tuned so much for the training examples that when I want to deploy it in a particular situation where the test samples will become slightly different from the training samples, my network will fail to classify. That's the situation in overfitting. So to avoid, CNN and RNN both have very neat trick to overcome this problem of overfitting. Next slide, please. Shikha, next slide, please. Yeah. So I just want to introduce to you what, convolution is a building block of a CNN, and this is how the convolution works, right? If you have worked with image processing, or if you worked with any signal processing, you will understand what convolution means. And as far as image processing goes, I have, let's say I'm taking a toy example, a 6x6 image, and I'm taking a 3x3 filter. The particular filter that you see here is known as a vertical edge detector, because the job is, if I want to do any image classification, I'll have to, the image can be any image. It can be your photo, it can be any scene, it can be a malware, it can be any it can be any matrix. Okay, basically it's a matrix. So let us call any matrix as a image. So I'm taking a 6x6 image, and I use a 3x3 vertical edge detector over it. So how do I convolve that? Take that vertical edge detector, place it on the 3x3 pixels on the top left corner of the image. Okay, multiply sample by sample and add them up. So it will be 3 into 1 plus 0 into 0 plus 1 into -1 and so on. So I'll have 9 multiplications. Add them up, I will get -5. There you can see on the left hand side, on the right hand side. So now what I'll do is I'll take this 3x3 filter and I will slide it one column at a time, and for every time I slide once, I'll multiply and add, I'll get one number. So what happens is I'll keep sliding until I hit the edge of the image, and once I've hit the edge of the image, the first row is done, and I will slide it row by row. So now what will happen is, if I do like this, if I slide like this, I will get a 4x4 matrix. I started with a 6x6 matrix input image. I'll end up with a 4x4 output. Okay, so this is all that convolution is all about. Okay, those who are having a signal processing background will know that this is not exactly convolution, but this is actually correlation. But convolution is safely, it can be safely, it's become the norm to use convolution here, and because it doesn't matter whether it is convolution or correlation, as far as CNN is concerned, the name stuck. Okay, so next slide, please. So this is all is about there to convolution. These are different examples of convolution. So let me just skip this slide. Next slide. Next slide. I'm just showing you what happens when you do a convolution. When I just convolve, this is just an example of, you can see when I convolve, on the left hand side, you can see two different images. On the top, you can see one half all tens and the second half all zeros. And on the bottom left, you can see first zeros and then tens. So that is basically white. In the top, it is white followed by dark, and the bottom you can see dark followed by white. So if I use vertical edge detector to convolve, you can see that the output I will get thick vertical edges. It is basically detecting in presence of any vertical edge. So if I want to detect a vertical edge in an image, then I go for this vertical edge detector filter. If I want to detect horizontal horizontal edges in the image, then I have to use a horizontal edge detector. I can use hand fixed values for the filter, or I can train them using back propagation. Doesn't matter. Next slide, please. Yeah, so if I see, remember I started with a 6x6 image, and when I convolve, I ended up with a 4x4 image, 4x4 matrix. Now you can see that the image has shrunk. If I don't want shrinking to happen, then all I have to do is pad it with zeros. Take the 6x6 image, pad it with zeros. If I just pad it with one layer of images, then I can retain the 6x6 output. Next slide, please. Yeah. So yeah, the striding. The next part is striding. So the striding is it depends upon the amount of accuracy that I want, and I can either shift sample by sample, or row by row, column by column, or I can choose to skip rows. So if I want to have a striding of 2, then it means that I'm skipping alternate rows. If I have a striding of 4, then I'm skipping 4 rows at a time. So that depends upon how the resolution at which I'm wanting to. The next slide. Yeah, so I made this point. Now so we've seen, yeah, this is fine. So now we've seen that we've convolved a 6x6 image. What if I have a color image, an RGB image? So that will have 3 channels. I'll have a 6x6 or 3 image. Then how do I convolve? Next slide. Next slide, please. Yeah. So this is, you can see an RGB image. You can see an RGB image, the previous slide. Yeah, you can see an RGB image here. It's a 6x6x3 because there are 3 channels. The moment I have a 3-channel input, the filter should also have 3 channels. So instead of having 3x3 filter, I'll have a 3x3 across 3 filter. That 3, the last 3 is the number of channels. So then convolution is exactly the same. Take the filter volume, place it over the image volume, multiply sample by sample for every channel, and add all the numbers. So instead of having 9 multiplications to add, now I have 27 multiplications to add, and I'll still end up with a single number. So that is why if you see, even though I'm convolving 2 volumes, the output would still be a 4x4 matrix. All right. So now what you're seeing on the bottom of the screen is that I have multiple filters. Specifically here, what I'm doing is I'm taking 2 filters. One for a detecting the vertical edge in the image, and the other for detecting horizontal edge in the image. So when I convolve them, when I convolve this RGB image with each of the filters, I will get 2 4x4 matrices as output. And all I'll do is I'll stack them up. Okay, I'll stack them up to get a tensor. That's all. So the output would be 4x4x2. So if I have, instead of having 2 edge detecting filters, suppose if I have 10 edge detecting filters here, the output would be 4x4x10. Is that clear? Next slide, please. Yeah. So so what you're seeing here is we have seen what happens in a conventional neural network. Remember what happens to a single neuron? Okay, what happens to a single neuron? I'm asking just you to scratch your brains and recall what we discussed earlier. You compute the weighted summation. Okay, Z is weighted summation of the inputs, and then you give it to an activation function, and that's the output of the network. A single convolutional layer is exactly the same. This is exactly the same. How? Look at this diagram. You have a 6x6x3 image. you have 2 filters, 3 cross 3 cross 3, 2 filters. So you do separate convolution for each filter, and you will have a 4 cross 4 matrix for each filter, right? What is 4 cross 4? How did you get this 4 cross 4? You have multiplied and added the by convolving the filter with the image. What is multiplying and adding? It's simply sigma. If my inputs are A's and if I consider the input pixel values to be A, and if I consider the filter coefficients to be W, then I'm simply doing sigma Wi Ai. That's exactly my Z value there. So sigma, what you did in a traditional neuron. Okay, so we have sigma Wi Ai. Now, then what do? We give it to what is known as the activation function called ReLU, which is very, very popular today. Not so much the sigma activation function, but the activation function that's very popular today is known as ReLU, or rectified linear units. Okay. Lack of time, so I'm not going to discuss to you what ReLU is. So ReLU is an activation function which speeds up your computation like nothing. It's super good, so ReLU is used. So you have ReLU. You apply ReLU on this Wixi, so that gives me that is my G of Z. That's my ReLU. So you can see that it's exactly what you do in a traditional neuron. Okay, next layer. Sorry, next. Yeah. So this is a typical convolutional neural network that I have. I'm just going to spend a little time on this and then quickly go to the next few slides. If you understand this, then you're going to understand the next few slides very quickly. I have just a minute. Yeah. So I have a, let's just say I have a 39 cross 39 cross 3 RGB image. All right. So what I do is I will give it to I will use a 3 cross 3 cross I'll use a 3 cross 3 cross 3 filter, right? Let's say that I'm going to have 10 such filters. I'll do convolution with 10 filters separately. For each filter, I will get a 37 cross 37 matrix. Now, because I'm using 10 filters, I'm going to stack this 37 cross 37 matrices, and I'm going to get a 37 cross 37 cross 10 tensor. That's a volume, right? Then this is one layer of convolution. It's done. Now I'll take this and then I'll give it to the next layer of convolution. Here I'm going to use, instead of 3 cross 3 filters, I'm going to use 5 cross 5 cross 3 filters. And let's say I'm going to use 20 filters. Now 20 filters are for detecting 20 different edges. So so now when I convolve with 37 cross 37 cross 10 tensor with 5 cross 5 cross 3 20 such filters, the output would be 17 cross 17 cross 20. That 20 is because I'm using 20 filters. Use one more convolutional layer. What happens? Pay attention to this slide, please. I'm going to use again 5 cross 5 cross 3 filters for the third convolutional layer. Now I'm going to use 40 filters. So the output I'm going to get is 7 cross 7 cross 40. Just look at the size of the tensors or the volumes as you keep convolving them in layer after layer. So what happens is the width and the height keeps shrinking, but the depth keeps increasing as you go down the convolutional layers. In a typical convolutional neural network, you will have some number of convolutional layers like this, and then what happens is you will take that 7 cross 7 cross 40 tensor and you will unravel them and unwrap them into an array. Unwrap them into an array. It's going to be a single array, a single column. So if you do that, you will get 1960 dimensional array. Okay, it's basically one column. You have flattened the values. So this is called a flattened output. Now what you do is, now what you're going to do is, your convolutional part is over. You take this 1960 values and you will feed them into 1 or 2 layers, just like what you did in a multi-layer perceptron. So you will have a fully connected 1 or 2 layers of fully connected network, right? Just like what you did in your multi-layer perceptron. And then once you have this, let's assume that you have 2 fully connected layers. like how we do in a multi-layer perceptron. Take that output, and the final output of a convolutional neural network would be a softmax layer. Okay, softmax. When I say softmax, it helps me to do better classification. ReLU speeds up the process without compromising on the on anything. So for all the other layers, I'll use ReLU activation function, and for the output layer alone, I'll be using a softmax activation function, because that helps me in better classification. Alright, so this is all that is there in a convolutional neural network. You have different variants. That's what we're going to see in the next few slides. Please go to the next slide, Shika. Yeah, so one more important point is that we'll have what is known as pooling layers. In between convolutional layers, we'll have what is known as pooling layers. What we do in pooling layers is that, once you get the convolutional output, you are going to, let's say I don't want to retain everything. I just want to retain the key parameters, because anyway you have detected the edges. So every box, if I'm going to divide the output of a convolution into boxes, every box is going to contain some key edge that has been detected. So if I'm just going to pull out the maximum value, it means that it is equivalent to telling that I have detected the key feature or edge that is present within that small box. So if you can see that I've divided this image, which is the output of a convolution, into 4 sub images, and in each sub image I'm just pulling out the maximum value. So I have just retained the key features from that image. That's all that pooling does. That's max pooling. Alternatively, I can do average pooling. Instead of pulling out the maximum value, I can take the average value. So that's you insert. This pooling is inserted between convolutional layers. Next slide, please. Next slide, please. Yeah, the next slide. The next slide. The next slide. I'm just skipping off all of this because I have to go to RNN. So these are some of the classical networks that we have. So what we have is what we saw was that hello.
Yes, ma'am. I
Yes,
think
sir?
we don't have time for RNN. Maybe you can just discuss about the
Hello?
applications in cybersecurity.
Hello.
Hello, ma'am.
Okay.
Am I audible?
Sure, sir.
Yeah,
Sure,
we
I'll do
don't-
that. What I'll do is I'll just discuss one case study, and I'll just discuss a case study and quit it. Yeah, I'm not going to. Okay, I'll just stop here, ma'am. Stop here, ma'am. Ma'am. Oh, hold on. I'll just go to the next slide, please. What I'll do is I'll just take a couple of minutes to tell the case study, and then we'll quit it. Next slide, please, Shika. Next slide, please. One slide up. The previous slide. This one. So I'm just going to conclude my discussion with this case study. How CNN has been used for malware classification. See, so that you understood CNN, how CNN works. This is just a cakewalk for you. So all you do is you have your binary file, malware binary file. Okay, so you take this malware binary file, and then you can and then what you do is you have this 8-bit vector coming from that, and then you put it in a matrix form. Take this 8-bit vector and you put it in a matrix form, you will get this grayscale. It look like this grayscale image that you see. Okay, so all you have to do is take this binary file and convert it into matrix form, and that's the grayscale image that you get. So what they have done in this particular case is I've taken specifically David Gilbert's work. So what he's done is he's taken 9 different classes of malwares. For example, I've just put 2. One is a Ramit, this malware is steals sensitive information, and then the second type of is the Kelios version 3, which is involved in spamming and stealing bitcoins. So you can see very well that the Ramit samples, the 2D, the matrices that you generate for Ramit and for Kelios are very different. So you can use this as images as input to this CNN, and that's what they have done. So convert basically take a binary file, malware binary file, convert it into a 2D array, and then give that as an input to the CNN. Next slide, please. So he did it for 9 classes of malwares, and he gave this to different CNN. This is one of the architectures that he has used in his study. So he just he reduced all of them, normalized all the images to 32x32 input, give it to CNN, and got the output. Next slide, please. Yeah, so this is the result that he got. You can clearly see the left side above. You can see the accuracy keeps increasing as you keep training the number of iterations, and on the right hand side above, you can see the error keeps reducing as you train. And on the bottom, what you're seeing is a confusion matrix. You can see how the accuracy has significantly improved over the other techniques. The accuracy that he got was close to 98%. Okay, so I have a lot more to say, but because of paucity of time, I have not been able to discuss an RNN. There was the case study 2 and case study 3 were pretty interesting, but unfortunate that due to lack of time and due to the different constraints, we were not able to go through all of these slides. So I'm sorry, I have to quit at this point of time. I hope it was an informative session. Thank you very much.
Thank you, ma'am. Thanks a lot for the session. It was very informative. Professor Anand, should I stop this session recording?
Yes. We'll stop this session. We'll share the slides with the participants. Ma'am, we'll share the slides with the participants. Some of the